Hello students, so the question here says figure below shows a spring fixed at the bottom end of an incline of inclination 37 degrees. A small block of mass 2 kg starts slipping down from the incline from a point 4.8 meters away from the spring. The block compresses the spring by 20 centimeters, stops momentarily and then rebounds through a distance of 1 meter up the incline. Find number 1 the friction coefficient between the plane and the block, and number 2 the spring constant of the spring. So, as we look at the situation, what is happening is this block that we have drawn here, because of the gravitational pull, it will slip down along the incline. As it reaches down here and touches the spring, it will press the spring due to its momentum, due to the kinetic energy that it has gained. In the process, it will compress the spring and will reach a position where the spring will be compressed by the maximum extent, and there the block will stop for a moment. So, I have shown that situation here. According to the question, the block, as it compresses the spring fully, it compresses it by a distance of 0.2 meters. So, we understand that the total distance starting from the position A, from where the block started off, to let us say the position B where the block stops for a moment, the total distance travelled by the block will be 4.8 meters plus the extra 0.2 meters, that is 20 centimeters, which the block presses the spring by, right. So, this will be the total movement of the block along the inclined plane, and 0.2 meters here will also be the compression suffered by the spring in the process of the block pressing the spring at the bottommost point of the block, right. So, the total distance, as we understand here, moved by the block in the process of moving down will be 5 meters, 4.8 plus 0.2. Now, after this point, what happens is the spring will push the block back up along the incline, and now as the block moves up, it is only able to travel a distance of 1 meter from the position B, from where it started off, and once again when it reaches this position C, 1 meter above the point B on the incline, it once again stops momentarily. Okay. So, in the later motion, in the upward motion, the block only moves a distance of 1 meter. This basically makes us understand that the surface of the incline is a rough surface. It is not a smooth surface, because had it been smooth, the block would have reached back to the point A after having rebound from the spring, because the energy of the block would remain conserved, right. So, we understand that there is a friction acting on the block, which will, as the block moves down, which will act in the backward direction. It will be kinetic in nature and will have a value of mu n, where n, the normal reaction of the block, will be nothing but the component of mg in the direction perpendicular to the block, which we all know will be mg cos theta, and it is the other component of mg, which is mg sin theta, which will take the block down the incline. So, these are the forces in the down, and this is the direction in which all these forces are acting on the block towards its downward journey, right. So, what we can do here is, since we know that the energy of the block is not conserved, the energy is being dissipated as friction is doing work on the block, we will not be able to use the conservation of energy principle, but we can still use the work energy theorem here. Yes. So, we can start by using the work energy theorem between the points A and B, the topmost point of the block and the bottommost point where it has compressed the spring by a distance of 0.2 meters, and we can from here get an equation, and then a similar equation we can get for the upward motion of the block back from point B to the point C. So, we will do it one by one. So, for the first type, which is the downward motion of the block, for the downward motion, we can say that using the work energy theorem, when used on the block between the points A and B. Between the points A and B, we see that the work done on the block will be by gravity. So, work done by gravity plus work done by friction. Friction will also do a work on the block, and if you see carefully, when the block moves after 44.8 meters, when it reaches the spring and starts compressing the spring will also do a work on the block for the last 0.2 meters of its motion. And that, according to the work energy theorem, should be equal to the change in the kinetic energy of the block between the points A and B, which if you look at carefully, at the point A the block was at rest, so its kinetic energy was 0. And at the bottommost point B, where it is momentarily at rest, there also the velocity of the block will be 0, so its kinetic energy will be 0. So that we know that change in kinetic energy of the block from the points A and B, in between the points A and B, will be 0. This does not mean that the block hasn't moved at all. It has moved. In fact, it gained velocity between the points A to the point where it just started compressing the spring. And once it started compressing the spring will deaccelerate the block and the block will once again come to rest, right? So, there is an acceleration and a deacceleration involved throughout the motion. Now, if we want to substitute the values for all these work done, there are a few things that we need to work upon first, and those things would be knowing the values of sine theta. Here theta is given to be 37 degrees. So, we all know that for a right angle triangle which has an angle of 37 degrees at the base, its three sides are of the ratio 3:4:5. So, looking at this right angle triangle, we easily see that sine of 37 degrees, which is opposite by hypotenuse, will be 3/5, and cos of 37 degrees, both of these terms we shall be using in our solution, it will be 4/5. Yeah. Having known this, now we can express these in the term of all the forces that we know. Work done by gravity. Since the block is moving along the incline, we can find out the component of gravity acting along the incline, which we can see from this figure here. It is mg sin theta. So, the work done by gravity will be the force of gravity along the displacement, which is mg sin theta, times, by the way, we can substitute the value of theta here, it is mg sin 37, times the displacement that the block undergoes, which is a total displacement of 5 meters. Now, we know this, right? Plus work done by friction. Friction is acting opposite to the displacement. So, the first thing is this plus will actually, it will actually be a minus sign here. The work done by friction will actually be negative. Negative of work done by friction is force of friction, which will be mu into n, where we know n is mg cos theta. So, mg cos 37 multiplied by the same displacement through which the block moves, which is 5 meters. This is the work done by friction, plus the work done by spring. In the process of the block moving down and compressing the spring by a distance of 0.2 meters, understand that the work done by the spring will be half k into 0.2 meters. Half k x squared is the work done by the spring. Here in this case, understand that the work done by spring will be negative, because as this block is compressing the spring will exert the force in the opposite direction to the motion of the block. So, the work done by spring in this case will be negative, and this we know the whole three terms together are equal to 0. Now, we can maybe substitute the values here. The block's mass is given to be 2 kg. So, its mg value will be 20 into sine 37 we know is 3/5 into 5. This becomes your first term, minus mu into mg is once again 20 into cos 37, which is now 4/5 into 5, and minus half k into 0.2 whole squared will be 0.04, which we can simplify in the next step now. So, as we see, there are a few terms cancelling out here, these 5s will cancel out. So, here we are getting 60 minus 80 mu minus 0.04 by 2 will be 0.02, k is equal to 0, and it is this equation that we can consider as our equation number 1 in two variables, k as well as mu. Now, we shall use the second condition and we will try to get another equation, similar equation, and then we will solve the two. So, now we come to the second scenario, where now the block, having started from the position B, is now moving back up the incline and it reaches till position C. Once again, we use the work energy theorem. Between this time the points B and C. So work done by gravity once again plus work done by friction plus the work done by spring will be equal to the change in kinetic energy, which this time will also be 0 because the block started off from rest, and C is also the topmost point of the block. So once it reaches C, it will again come at rest, right? So the right hand side of the equation is 0. Work done by gravity in this case, understand, will be mg sine 37, the force of gravity along the direction of incline, times the displacement, which is this time 1 meter only. But see that the work done by gravity this time will be negative, as the force of gravity is acting down the incline, whereas the motion of the block is up the incline. So this work will be negative by gravity this time. Plus work done by friction will once again be the frictional force, which is mu mg into cos 37 times the displacement, which is 1, and of course this will be with a minus sign. Work done by friction will be negative because when the block moves up, frictional force will also act in the downward direction opposite to the displacement. So both mg sine theta as well as friction this time act downward, whereas the block is moving in the upward direction. Plus the work done by spring, once again half kx squared, and this time with a positive sign. Why? Because the spring, as it pushes the block up, the block moves up, right? So the force of spring and the motion of the block are in the same direction, so it will be a positive work by the spring. This x value we already know, it is 0.2 meters. The amount by which the block had compressed the spring will once again open up by the same amount, right? And these three terms together will be equal to 0. Now we can simplify this equation, once again substituting the values. So it will be minus 20 into sine 37, which is 3 by 5, times 1, which will go minus mu into mg is 20 and cos 37, which is now 4 by 5, plus half k into 0.2 squared, which is 0.04. This term is equal to 0. Simplify it further to get the second equation, which will be like this. This will be minus 12 and this will be minus 16 mu plus 0.02 k is equal to 0. This becomes our equation number 2, right? Now if we just compare the two equations 1 and 2 that we have written, we see that the k term contains the same variable, the same constant before it. So if I just write down the first equation once again down here, I can call it equation number 2, and now I can beneath it write the first equation 60 minus 80 mu minus 0.02 k is equal to 0. This was our equation 1. Do you see we can very easily now solve for the mu value here just by adding the two equations, because adding the two equations will cancel out these two terms containing k, and we will directly get 48 minus 96 mu is equal to 0, which gives you mu is equal to 48 by 96, which is nothing but 1 by 2 or 0.5. Substituting this mu value now back into any of these two equations will give you the value of k. So let's say we substitute it in the first equation, minus 12 minus 16 into 1 by 2 will be 8 plus 0.02 k is equal to 0, solving which you will get the value of k as 20 by 0.02, which is nothing but 1000.